This is a video for AQA Mechanics, Center of Mass and Moments, section 2.1, which looks at the equilibrium of a rigid body. The diagram is just illustrating the fact that if we have a rigid body, it may well have several forces acting on it. But if we want to consider that the body is in what we call static equilibrium, then we have a couple of results that must apply. Firstly, that the resultant force in any direction must be equal to zero. So the sum of these forces, for example, in this direction, which might be called the x direction, and in this direction, y direction, so we could say that the sum of the forces in the x direction must be equal to zero, and the sum of the forces in the y direction is equal to zero. And also, we can take any point on the body whatsoever, or even outside the body, and the moments about that point must sum to zero. Now, if that wasn't the case, if, for example, we had forces that didn't sum to zero in one direction, then we would have a net force in that direction, and therefore we'd get an acceleration. Or alternatively, if we had forces which gave a net moment about a point, then the body would itself turn about that point. So therefore, for equilibrium, these two facts must hold true. Now that allows us to write three equations for any given situation, and if we've got three equations, we can therefore solve up to three unknowns. So for example, we could solve a problem by resolving in two directions and taking moments about one point, or we might resolve in one direction and take moments about two different points. Or alternatively, although quite rare to be honest, is the fact that we could take moments about three different points. The choice of points for taking moments is actually worth considering quite a lot when you're thinking about a problem. The reason for that is if we've got unknown values, for example, we might have a situation where at some point we've got moments where we've got unknown values at that point, then if we take moments about that point, then those forces produce zero moments. And therefore, quite often what we do is take moments about a point where we've got lots of unknown forces acting, and those forces become irrelevant in the equation. And we'll see that in some of the examples that we're looking at in a minute. So here's a question point where we've got a rod, mass 5 kilograms, length 3 meters, and it's hinged at point A. Now the mass, of course, is, if it's a uniform rod, is going to act at the center, so we can say that there's a force here of 5G acting at the center, and it's supported by a cable with some tension T that we're asked to find. Now there are other forces acting. Those are forces which are acting at the hinge here. Now we don't necessarily know which direction those are going to act in, so one way of considering this is to split those into two forces, X and Y, which in some questions we may need to find. But for this question we're asked to find the tension, so an obvious choice of point is A to take moments about. So taking moments about A, we can say that the anti-clockwise moment is given by T, and if we consider that, well, one way is to resolve T so that we look at its vertical component, so that there is 50 degrees, so we can say that T cosine 50 degrees multiplied by the distance. We're told in the question that the rod has got a length 3, so T cos 50 multiplied by 3 must be equal to the moment in the other direction, the clockwise moment, which is divided by 5G. So 5G and its distance is 1.5. The X and Y, the forces that we're unsure about at the hinge, those don't come into this because we're actually taking moments about that point, and both X and Y act through A. So therefore t must be equal to 5g multiplied by 1.5, so that's 7.5, which is 5 multiplied by 1.5, and g 9.8, and divided by 3 times cosine of 50 degrees. And if you calculate that, we get an answer of 38.1 newtons. The second part of the question asks us to find the total reaction force at the hinge. So we've got our value of T equal to 38.1 newtons, and we're considering the reaction as being made up of two components, X and Y. So then one way of doing this is to resolve horizontally first of all in the X direction. So we can see from that we've only got the two forces, the component of T, which is T cosine 40 degrees, that must be equal to X. And this gives X equal to a value of 29.2. In the vertical direction, then we've got upwards Y and the other component of T, which will be T sine 40 degrees, and that must be equal to a value of 5g, which is the component, which is the weight which is acting downwards. And therefore y is equal to 5g minus T sine 40. Y equals 5g minus, remember we know that T is 38.1 sine 40. And that gives a value of y equal to 24.5 newtons. Once we've got X and Y, we can then say that the reaction force R must be equal to the square root of X squared plus Y squared, so this is using Pythagoras' theorem obviously. And if you calculate that, the square root of 29.2 squared plus 24.5 squared, then R turns out to be 38.1 degrees. 38.1 newtons. Now you might think that that's a strange coincidence that it's 38.1 newtons. However, there are other ways of completing this question, and one way would be to say, well, instead of considering the reaction force as two components, we could consider it as a single force R, and because then there are only three forces acting on the bar, these three forces must act through this single point here, so that then we have a reaction force which must be equal to the tension, because then we have an isosceles triangle. So we can see that the forces, the 5G, T and R acting through this single point here, must mean that R is equal to T. Now that second method was relatively straightforward because the weight of the object being uniform was acting at the center, and therefore we ended up with an isosceles triangle. However, it is not always the case that the weight is acting at the center, and we'll have a look at a question like that in a second. In this second example, we've got again a uniform rod, mass 5 kilograms and length 3 meters, but this time the center of mass is at 2 meters from A, so the 5G weight is acting at this position here, where this is 2 meters and this is 1 meter. The reaction forces at the hinge, again, we can consider as X and Y, but if we take moments about A, the hinge, then they don't come into our equations, and we can look at the moments clockwise and anti-clockwise. So considering first of all the anti-clockwise moment, that's provided by T, and you can see that T is acting at right angles to the bar this time, so that we have in the anti-clockwise direction a moment of T multiplied by 3. In the clockwise direction, that's a moment provided by 5G, So if we work out the distance perpendicular here that the 5G force acts compared to A, then we can see that this angle here is 30 degrees, so the distance is 2 cosine 30. Therefore, the moment is 5G multiplied by 2 cosine 30 degrees. That gives a value of t equal to 5G multiplied by 2 cos 30 divided by 3, which turns out to be 28.3 newtons. Now this is a case in point where it would be far more difficult to work out the point at which the normal reaction, the reaction at A acts, because if that's a single force, it would again act through a point where these two forces here meet, must act through this point because there are only three forces acting. However, it's not so easy this time to calculate that, so therefore resolving horizontally and vertically, should you need to find x and y, would probably be the easier method. That concludes this video. In the next one we'll be considering the idea of ladders.